Hey there. Let's talk about IEEE 754 floating point numbers stored inside of your machine. What the heck am I even talking about? Well, there's a standard called IEEE 754, which governs how floating point numbers are stored inside of your computer on x86-64 machines. So, at this point of watching this video, you probably already know how to convert binary back and forth, between binary and decimal, and hopefully you understand how to do binary with fractions. If you don't, I have other videos. I'll talk about that in a second. And you also understand that in the machine, there is like a slightly different format. That's my doggy. Slightly different format for storing signed integers in the machine. Okay, so floating point numbers have an even different format that we have to follow. And the hardware is designed that way. So before we can really benefit... You're all going to see how bad I spell. Okay. Before we can benefit from this video, your prerequisite knowledge should be that, for starters, you should be able to convert back and forth between binary and decimal, including numbers with fractions. So if you don't know how to do that yet, this video is not for you just yet. You should go check out my other videos. I explain in other videos exactly how to do that. Go to the other videos, come back, and then check this one out after you know how to convert back and forth between binary and decimal with fractions. The second thing you should know how to do before watching this video is convert binary numbers with fractions to scientific notation and back again. Meaning, you should understand scientific notation, and you should also understand how to take a binary number with a fraction and convert it to scientific notation, and then convert it or deconvert it back to like regular form. Again, I have another video for this, so if you don't know how to do that yet, you should probably pause this video and then go find my other video and check that out. Okay, so the basic steps, let's see, for converting from a regular number to IEEE floating point number in the machine using just binary alone is the following. So I'm going to say basic steps. Whoops. Okay. Step 1, convert the decimal number to binary if needed. And I say if needed because, I don't know, maybe you started with a binary number, so you don't actually need to convert it. But I'm just going to assume that you have a decimal number, so you're going to convert it to binary first. Then convert the binary number to scientific notation. I don't know if convert is the right word here because we're not actually changing the value of the number. We're just changing the representation. So convert it to scientific notation form maybe would be better. Step 3, we'll add a bias to the exponents of the scientific notation form. What do I mean by that? If you have like a binary number and it's in scientific notation format, it's going to look like this. I liked, when I'm doing IEEE 754, I like to keep the right side of the number in decimal. I'm sorry if this confuses you, but it's not really necessary to convert this to binary when we're just trying to convert back and forth between IEEE. So I always say 2 to the something power rather than 10 to the something power because I want to stay in decimal. So I'll say, 2 to the 7th power, right? What this means is that 7 is the exponent, and I have to bias the exponent before I put it into the machine. So maybe it's worth understanding, or maybe copy pasting right now, that the bias for 32-bit floating point numbers, I'll paste the whole thing here. Okay, so here's like the format for a 32-bit floating point number. Forget about this just for a second. The bias for 32-bit floating point number in IEEE 754 is 127. So that means I pretty much have to just take the number 7 and bias it by adding 127 to it. After I've done that, I can convert the biased exponent to unsigned binary whole number to an unsigned binary whole number. So step 4 here is just regular decimal to binary conversion. So I would take 7 plus 127. The result of that, which I think is like 134 maybe, will just be converted into binary, an unsigned binary integer, not 2's complement or anything like that. Then step 5 is respect the layout. So I just copy pasted the layout up above, and the layout is this. You can see that here, let me see if I just maybe paste this down at the bottom. You can see that we actually have 32 bits here. If I count them for you real fast, we've got 1 for the sign, and then we've got, oh, I can never remember this. I think it's 8 for the exponent. 1, 2, 3, 4, 5, 6, 7, 8. Got 8 bits for the exponent. That means I've already used 9 of 32 bits. So that means I should have like 23 bits here. So 1, 2, 3, 4, 5, 6, 7, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, just to double check. So we know what the sign bit is. Actually, we don't yet know in this video. So in this video, the sign bit, it's always going to be a 0 if the number is positive and a 1 if the number is negative. So that's the sign bit. The biased exponent bits go there. And then these Fs, those are just the fractional bits. The bits that are just the, like the mantissa or the mantissa part of the fraction. So imagine if we have a number like this. All I'm saying is we would copy paste those numbers right here. Notice how I'm ignoring that first 1 dot something, because when you put binary in scientific notation, the first number is always going to be a 1. So it can be assumed. There's no point in storing it inside the machine. And then if you don't have enough digits to account for all of the fractional bits, you will literally just pad with zeros on the right side, because padding with zeros on the right side of a fraction doesn't actually change the value. 1, 2, 3, 4. If I put the zeros on the left side of the fraction, it would make the fractional part smaller and smaller, so that would be bad. I don't want to change the value. And this is the opposite of how you pad a whole number. If I put numbers on the left side of a whole number part, I'm not changing the value, but if I put numbers on the right side of a whole number part, which in this case would be the biased exponent, then I would be changing the value, so we wouldn't want to do that. Anyway, I'm going to remove this and just stick with step 5. So let's see. 5a is place the sign bits. Step 5b is, and I'm going to do an example for you, don't worry. Place the exponent bits. And then 5c is place the fraction bits. Everything after the first 1 dot. From scientific notation form. Again, because the first 1 is implied, it will never be a 0 if you've done it correctly. If you end up with a binary number that looks like this in scientific notation, then you've done something wrong, because the first number is supposed to be a 1. Okay, so we have those basic steps, and now let's do an example. So here's an example. 1, 2, 3, example. Let's convert decimal to IEEE 754 32-bit float format, aka single precision floating point number. Double precision floating point number is 64-bit. We'll do an example for that at the very end of this, but I'm just going to stick with 32 and do the hard work here. So suppose we have the number 45.84375, 84375, just double checking. And then we'll convert to binary. Again, this knowledge is contained in a different video. So if you don't know how to do this yet, you'll need to go see my other video. And so you can see it's 45.84375 in binary is just going to be this. I've padded it with 2 zeros to the left just because, I don't know, I have a habit of wanting everything to look like it's inside of 8-bit chunks. You can see there's 8 bits here, but really I can just remove those first 2 numbers. It doesn't matter. Convert the number to binary. Then I have to convert the binary number to scientific notation. I'm going to put maybe pseudo scientific notation, because I'm not going to convert the right part where it's the exponent into binary. I'm going to keep it in decimal. Just to clarify again, if you were going to convert a binary number to scientific notation and you were actually going to publish it somewhere or give it to someone, then you should convert the right side. It's just that I'm not going to, because I don't really need to convert the right side. I'm not interested in having the whole number in scientific notation in binary. I'm just interested in what the fractional bits are, and then what the exponent is going to do. Like how many positions to the left or right is it actually going to move the decimal point, and that's just going to be the number 5. 5 times to the left or to the right. So I'm going to go pseudo scientific notation. You pretty much as I covered in a different video, all we're going to be doing is just moving the decimal point over 1, 2, 3, 4, 5 until there's a 1 in the leading spot, and then account for it by saying times 2 to the 5th power to say the number is a lot bigger than it looks. So that's that. And let's see, if there are any trailing zeros, that's okay on the right side of the fraction. They don't actually matter. You can also just delete them if you want. Then we need to bias the exponents. So how do we bias the exponent? The exponent is just the number 5. See, I was telling you, like, I don't really care to convert it to binary because I'm just going to bias it first, and then after that I'll convert it to binary. So biasing it is just basically adding the bias. I should probably copy the layout here just to make sure that it's on this page and it's easy to see. So I'll do that. So in the 32-bit float layout, the bias is 127. So I'm going to add 127 to 5. The final number is going to be 132. So that's the biased exponent now. Then I convert the biased exponent to binary, and that's going to be this 100000100. Then set up the layout so you don't get confused. This step is crucial. Everyone always gets confused by the layout because, like, we're human beings. I can't count 32 zeros that are all like in the same area and like, you know, and not get confused every single time. I mean, I guess I won't get confused half the time, but that's not good enough. So step 1 is place the layout for yourself so it's easier for you to place the bits. And I wrote this at the top, 8 bits and 23 bits, just as a reminder. Double check yourself. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. 1, 2, 3, that's 23 bits. 1, 2, 3, 4. 1, 2, 3, 4, that's 8 bits. We don't need to remember that the sign bit is 1 bit for now. It's not too hard. So now let's place it. So the first thing to note is that this number was actually positive. Positive is implied in IEEE unless you have the negative sign there, but if it makes you feel better, we'll just put a positive sign there just to clarify and be specific. So because the number is positive, the sign bit is going to be 0. If it were negative, it would be 1. Then we will put the biased exponent bits. So we already converted up there, so I'm just going to copy paste it here. We're pretty lucky that the bits are just as big as the number of biased exponent bits that are available. But suppose for the sake of argument that we had just like, you know, this small number here for the biased exponent, what would you do with the remaining spaces? You would just pad with zeros to the left. Because remember, in whole numbers, in binary and decimal, if you pad to the left, you're not actually changing the value. You definitely would not want to pad to the right. But you got to put a bit in every position. It's got to be something. So I'm just going to pad with zeros. Then we take the fractional part from the scientifically notated form. So that's just this right here. Notice how I'm copy pasting every bit except for the one that starts the number. I'm not going to do the 1 dot part because that's always assumed. So we don't need to store it. It wouldn't make sense. I'll copy paste the fractional part and I'll just stick it down there. And now we have a bunch of leftover bits that we need to fill out. With the fractional part, you pad to the right, not to the left. So I'm just going to put zeros to the right because that won't change the value of the fractional part. Now we've got it. I'm just going to double check my work here. 1, 2, oh gosh. It's too hard to read and then a bunch of zeros. Okay. Then remove these spaces because now that you've done your layout, you actually want to bear in mind that the machine doesn't have spaces. The machine is just, you know, bunch of 1s and 0s everywhere. So I'm just going to carefully remove the 2 spaces. And this is it. This is our final IEEE 754 floating point representation of the number, of the decimal number, positive 45.84375. Seems like a lot, but it's not too bad once you kind of get used to the format and the bias, and you already know the other steps of, you know, converting decimal to binary and back again. So let's do another number. Let's do it backwards. So I'm going to open up a new tab here, and I'm going to say example IEEE 754 32-bit float to decimal. Okay, so suppose we started with the following number. Start with this number. Oh my gosh, right? Remember the layout. So in the layout we have, use the layout. Maybe I should copy paste the layout again one more time just to make sure that it's easy to see. So I'm going to paste it up at the top. And, well, no, maybe I want this because this is like a little bit better. I want that version. Okay, so 32 bits, a bias of 127. So we're going to use the layout. I'm just going to copy paste the original number and then add spaces because I know, well, I guess I can copy paste the layout itself right above that number. I know I need a space right there, that's the sign bit, and then I need a space after that. And notice how the numbers all line up, so there's nothing missing, just to double check yourself. Okay, so I have the layout. I know right away that the number is going to be positive because the sign bit is 0. Sign is positive. Okay, so then I need to pull the biased exponent. Pull the biased exponent. And so that's just going to be the exponent bits only. So I'm just going to copy paste those bits. And then I'll pull out the fractional part first. Pull out the fractional part. I'm going to copy paste all those bits. And maybe I'll just say 0 point those bits because that's what I originally grabbed. And I can delete all the zeros on the right side because, again, that won't change the value of the fractional part. So I'm going to delete. Make sure you're only deleting zeros, though. Delete that. Now, I need to unbias the biased exponents. First, actually, I should, well, let's convert the biased exponent to decimal. A little easier. I guess you don't have to do that, but it's a little easier for me. Pull the biased exponent. So this number is going to be 132, which I think is what we had last time. Let me just double check that. 132, yeah. So the biased exponent that we pulled out is 132. Then we unbias the biased exponent, so just subtract the bias. Again, in 32-bit format here, the bias is 127. So I'm going to subtract 127 instead of adding 127. So now I know the real bias, or sorry, I know the real exponent is 5. Then I can recreate the binary number in scientific notation. I'll put pseudo here just because it's not, I'm not converting binary for the entire thing. So that means I can take the fractional part here and I can say it's going to be 1 dot the fractional part. Maybe I should remove that 0 here to make it less, I don't know, because if I put a 1 there, it kind of feels like I'm saying the number is 0 dot something, but we know that it's 1 dot something. I don't like that I'm putting a 0 there. I'm just gonna erase it because it's really going to end up being a 1. And if I say pull the fractional part and I put a 1 there, then doesn't it kind of sound like I'm pulling the 1 from somewhere? No, the 1 is implied. Anyway, so now I can recreate the number in pseudo-scientific notation. I can say times 2 to the something power. We know that the exponent is 5. Again, it's pseudo-scientific notation because if I were going to do the complete, true scientific notation, the right side should also be in binary. But I'm not going to do it. I'm a little bit lazy because we don't need that for IEEE. So it's going to be 2 to the 5th power. Then if I undo the scientific notation, I'm really just going to take the scientifically notated version and I'm going to say, well, I'm going to move the decimal point to the right 5 times because that's what the part on the right says. So I'm going to go 1, 2, 3, 4, 5, stick it there, remove the original decimal point, and then I can remove the exponent part. So then let me just double check my work. 101101 1101. Okay. So we've got that now. Then all we have to do is convert this number from binary to decimal. The final number here is just, it's going to be the same number that we worked with previously. So I'm just going to copy paste it. There is, of course, this video is not about converting back and forth from binary to decimal with fractions. Check out my other video if you want to learn how to do that. But once we do that, this number becomes that number. And now we know how to convert back and forth between a decimal number and IEEE 754 32-bit floats in the machine. No problem. A lot of steps, but no problem once you understand them. Okay, now let's do an example with 64-bit floating point numbers. Honestly, this is not going to be more difficult in 64-bit floats, the idea and the format and the steps, it's all going to be the exact same thing. It's just that we have more bits for the biased exponent and the fraction, and then the bias itself will be a little bit higher. So let me copy paste the format for you to see. So in IEEE 64-bit floats, IEEE 64-bit float, well, IEEE 754, 64-bit float. We refer to these floats as doubles, right? Double precision floating point numbers. Notice how instead of 8 bits for the biased exponent, we have 11, so we can represent a much larger number. And also notice how for the fraction part, instead of having 23 bits, we have 52 bits. So we can also represent much more precisely. That's really the only difference. Let's, the other difference is also that the bias is now equal to 1023 instead of 127. So what is that, like 10 times larger of a number that we can represent or something like that? So mostly we get more precision. If you don't like it, sorry, it's the way it is, it's in the hardware. So let's do an example for a 64-bit float, for a double. 64-bit example. Let's say we started with the following number inside of the machine. Like we looked inside of the machine and we grabbed these bits. And I'll get rid of the spaces. So we have like a giant, big, huge number. We're trying to figure out, what is this number in decimal? So I'm going to add spaces to respect the layout. I'm going to just copy paste the layout right here. I'm going to say respect the layout. I'm going to paste it, and then that helps me line everything up. So I'm going to say the sign bit is the first bit, and then I'll put a space there so I know, all right, the sign bit is a 1. That means it's going to be a negative number. The biased exponent bits are there. The fractional bits are there. So, well, first thing I can just do is say that the sign is going to be negative because the sign bit is a 1. And then I'll pull the biased exponent bits, which is going to be this number right here. If I convert the biased, well, maybe I should pull the fraction bits next. Fraction bits are just here. I'm going to copy paste those here, and then I can remove the zeros. Be very careful you're not removing any ones. So there was a lot of wasted bits there. That's okay. I'll convert the biased exponent to decimal. So that's going to be, this number becomes 1031, I think. And I did not do that in my head. I have an answer sheet. Don't worry. I'm not that cool. Then we'll unbias or debias. Unbias the biased exponent by just subtracting the bias. Remember, in this 64-bit format, the bias is 1023, so that means I got to take 1031 minus 1023, and that will be equal to 8. Okay, now we kind of have everything we need to sort of reconstruct the scientific notation part, right? We have the fraction bits, that's the most important part. Oh, and then also the sign bit. So I can say negative something. It's obviously going to be 1 dot something, because even though the number is negative, it will still always start with a 1. That rule doesn't change. Negative 1 dot something, and I'll just paste the, paste the fraction bits. I think I did paste the right thing. So we paste the fraction bits, and then we have to use the regular exponent, the unbiased exponent, the non-biased exponent, 2 times 2 to the, times 2 to the 8th power. Now this is our number in scientific notation. Convert to scientific notation. I'll put P for pseudo-scientific notation. And then, now we have to convert to just regular format. Okay, so I'm going to copy-paste this right here. And if it's 2 to the 8th power, that means the real number is going to be bigger than it looks in scientific notation, even though if you are very familiar with scientific notation, you kind of already know that it looks big. But if we're only talking about the bits on the left, we'll move it over to the right 8 times. 1, 2, 3, 4, 5, 6, 7, 8. Put the decimal point there. remove the original decimal point. Now we no longer need 2 to the 8th power. And again, just as a reminder, if it was 2 to the negative 8th power, you would be moving the decimal point in the other direction. So now we've got this number 111010101, then a 0.01. Okay, so then convert to decimal. And again, this video doesn't talk about how to convert back and forth from binary to decimal. Find my other videos, but basically it's going to end up being negative 469.25. Okay, we now have done a quick practice, starting with a giant number of bits and slowly converting them to the real floating point number in decimal that they represent. I'm not going to do another number in the reverse direction because we already did that for 32 bits. And again, with 64 bits, the only real difference is just you have more exponent and fraction bits, and the bias is a higher number, and that's it. So like all the other steps are just the same. I just wanted to show you one time with a 64-bit number in one direction, but I think at this point we're good. Thank you so much for watching this video. I hope you learned a little bit of stuff, and I hope you had a little bit of fun. I'll see you in the next video. Hey everybody. Thanks for watching this video again. From the bottom of my heart, I really appreciate it. I do hope you did learn something and have some fun. If you could do me a small little favor, could you please subscribe and follow this channel or these videos or whatever it is you do on the current social media website that you're looking at right now. It would really mean the world to me, and it'll help make more videos and grow this community. So we'll be able to do more videos, longer videos, better videos, or just I'll be able to keep making videos in general. So please do me a kindness and subscribe. You know, sometimes I'm sleeping in the middle of the night and I just wake up because I know somebody subscribed or followed. It just wakes me up and I get filled with joy. That's exactly what happens every single time. So you could do it as a nice favor to me, or you could troll me if you want to just wake me up in the middle of the night. Just subscribe and then I'll just wake up. I promise that's what will happen. Also, if you look at the middle of the screen right now, you should see a QR code which you can scan in order to go to the website, which I think is also named somewhere at the bottom of this video. And it'll take you to my main website where you can just kind of like see all the videos I published and the services and tutorials and things that I offer and all that good stuff. And if you have a suggestion for clarifications or errata or just future videos that you want to see, please leave a comment. Or if you just want to say, hey, what's up? What's going on? You know, just send me a comment. Whatever. I also wake up for those in the middle of the night. I wake up in a cold sweat and I'm like, it would really mean the world to me. I would really appreciate it. So again, thank you so much for watching this video, and enjoy the cool music as I fade into the darkness, which is coming for us all.